Capacitors that rapidly store and release electric energy are key components in modern electronics and power systems. However, the most commonly used ones have low energy densities compared to other storage systems like batteries or fuel cells, which in turn cannot discharge and recharge rapidly without sustaining damage. Now, as reported in the journal Science, researchers have found the best of both worlds. By introducing isolated defects to a type of commercially available thin film in a straightforward post-processing step, a team led by researchers at the Department of Energy's Lawrence Berkeley National Laboratory has demonstrated that a common material can be processed into a top-performing energy storage material. The research is supported by the Materials Project, an open-access online database that virtually delivers the largest collection of materials properties to scientists around the globe. Today, the Materials Project combines both computational and experimental efforts to, among other goals, accelerate the design of new functional materials. This includes understanding ways to manipulate known materials in ways that improve their performance. Growing requirements for cost reduction and device miniaturization have driven a push toward development of high energy density capacitors. Capacitors are commonly used in electronic devices to maintain power supply while a battery is being charged. The new material developed by Berkeley Lab could ultimately combine the efficiency, reliability, and robustness of capacitors with the energy storage capabilities of larger scale batteries. Applications include personal electronic devices, wearable technology, and car audio systems. The material is based on a so-called relaxer ferroelectric, which is a ceramic material that undergoes a rapid mechanical or electronic response to an external electric field and is commonly used as a capacitor in applications like ultrasonics, pressure sensors, and voltage generators. The applied field drives changes in the orientation of the electrons in the material. At the same time, the field drives a change in the energy stored in the materials, making them a good candidate for use beyond a small-scale capacitor. The problem to solve is how to optimize the ferroelectric so that it can be charged to high voltages and discharged very rapidly, billions of times or more, without sustaining damage that would render it unsuitable for long-term use in applications such as computers and vehicles. The researchers accomplished this by introducing local defects that allowed it to withstand bigger voltages. Placing a ferroelectric material between two electrodes and increasing the electric field causes charge to build up. During discharge, the amount of energy available depends on how strongly the material's electrons orient or become polarized in response to the electric field. However, most such materials typically cannot withstand a large electric field before the material fails. The fundamental challenge, therefore, is to find a way to increase the maximum possible electric field without sacrificing the polarization. The researchers turned to an approach that they had previously developed to turn off conductivity in a material. By bombarding a thin film with high energy charged particles known as ions, they were able to introduce isolated defects. The defects trap the material's electrons, preventing their motion and decreasing the film's conductivity by orders of magnitude.